Okay, 5.1 is probability distributions. So we've talked about the different kinds of distributions, and the distributions come from graphing a histogram. So we are going to do probability distributions, and this is going to help you on your project for chapter 4 and 5. So just to review, theoretical probability is using probability of an event occurring based on what would happen in theory. So this is what should happen. If there are 6 numbers on a spinner, probability of getting a 1 is 1 out of 6. Probability of getting an even is 3 out of 6, which is 1/2. So we are going to look at the distribution of probabilities. Empirical probability is experimental, what actually happens. So that's experiments or observations. So the first term that we're going to look at is a random variable. So when we spin a spinner, a fair spinner, or roll a die, we are able to come up with a random variable. So random variable, which is, I'll abbreviate with just RV, is a variable that we're going to call x. So variable x that has a single numeric value determined by chance for each outcome of an event. So my random variable for my experiment, whenever I did it, was how many, how many evens I got. So here were our 2 spinners. How many evens I got was what I wrote. So I'm going to show you this a little later too, but my x is how many evens I got. So here are the 2 spinners. I do both spinners. I look at the 2 numbers. If I get 1 even, then it goes under here. If I get 0 evens, it goes here. If I get 2 evens, it goes here. So I'm going to show you more on this as we go along. So probability distribution is a distribution that gives the probability for each random variable x. I'm going to abbreviate random variable. So we can write this as a graph, a table, or a formula. We are going to use a histogram or a bar chart. I'll put chart as well. So the way we first express it is with a table. So here's our first probability distribution chart or table. So the example is 12 jurors are to be randomly selected without bias from a population in which 80% of the jurors are Mexican American. So there's some kind of court going on. So we've got to select the jury, and you have 12 that need to be selected. And so this is the probability of how the jurors will be selected. So X represents how many Mexican Americans are chosen in the 12. So it says if we let X equal number of Mexican American jurors among 12 jurors. So your options are you could have 1, You could have 2. You could have all the way to 12. So 12 would be if all of them were Mexican American. So in the beginning, of only having 1 is 0 plus. So that 0 plus, if you look here, it's just a really, really small number that we can't express with 3 significant digits. It's more. Like we'd have to do a lot more zeros there. So that would just be 0. The probability would be 0 there. So of having 4 chosen out of the 12 is 0.001, and you can see the rest of them. So which one has the highest? Yeah. So 10. 10's the highest chance. So 10 out of 12 are selected, and it has a probability of 0.283. Let's look at what kinds of random variables we have. We're first going to talk about discrete random variables. So we've talked about discrete and continuous. We talked about it in college algebra. We might have talked about it a little bit in statistics. I don't remember. But discrete means that we have a countable number of them. So a finite collection of random variables. So this is also countable. You can make a list of them. Just like how many Mexican Americans there are, we make a list. You can't put a decimal in there. It's not continuous because that would be like 0.125 Mexican Americans. Like that, we're counting a Mexican American, period. One person. So an example would be, let X equal the number of eggs that a hen lays a day. So we can count the number of eggs, right? So an example, so X could be 0, 1, 2, 3, and so on. We can make a list. So I can also put it here. Make a list. Whenever it's discrete, you can make a list of all possible outcomes. Example 2, let X be the number of students in this class. So right now there are 12 in this class, but if everyone was here, or if there were more people that were supposed to be here, it'd be like that. We would count. We could count. We could make a list. I could look at the roster and count everyone. Okay, so the opposite of discrete would be continuous. So continuous, you can't make a list of them. You can't count them. So it's infinitely many X values or random variables. So continuous is a little bit more complicated. So I'd put down here non-countable. So the first example of a continuous random variable is let X be the amount of milk a cow produces in a day. So we couldn't make a list, but instead we could write it as an inequality. So X would be greater than or equal to 0. Any number that's greater than or equal to 0. Let X equal the measure of voltage for a particular smoke detector, the battery of it. So on this one, we can think about percentages of the battery remaining. So for this, X is between 0 and 100%. So I could say it's 22.35% battery remaining. So it's continuous. We can't make a list of all possible values because it's infinite. So let's look at these examples and see if you can figure out if it's discrete or continuous. Number 1, speed of an airplane. Can I make a list of the speeds, or is it more of a range that I can write as inequality? What do y'all think? It's like a range, yeah, because it is continuous, yeah. The number of ships in Pearl Harbor on any given day. Is it a range? Or can we make a list? Can we list them all? What do you think? Yeah, you can list them. You can go out there and you can count them, right? So it's countable, so it's discrete. The distance a golf ball travels after being hit with a driver. Continuous, yeah. We can't make a list of all that. It's infinite. The eye colors of players on the New York Giants. We could make a list, but is it numeric? No. So thinking back here, so that was a little thing to kind of throw you off, because we know that random variable has to have a single numeric value. So that would be neither. If they said number of people with brown eyes, like we could do that because we can count the number of people with brown eyes. It has to be numeric. The number of lightning strikes in Rocky Mountain National Park on a given day. Yeah, discrete. We can count that. All right, so we have to determine if the random variables, along with the probability of that random variable, represents a probability distribution. So we have 3 things you have to check. So number 1, there's a numeric random variable x, and its values are associated with corresponding probabilities. So basically, you're looking, is there a table like this? For your project, you're going to do x on the left side and p of x on the right side, where p of x represents the probability of getting x, that random variable. Number 2, the summation. Remember, summation means all of the px's added together equals 1. Think about probability. 1 in probability means 100%, right? So we've got to make sure that these probabilities add up to equal 1, because percentages and probabilities can only add up to equal 100%. So sum of probabilities equals 1. The third one is 0 is less than or equal to px is less than or equal to 1. So it's saying the probabilities are between 0 and 1. Because if any of these random variables has a higher probability than 1, that doesn't work, right? So it has to be a number between 0 and 1. All px, all probability of x, are between 0 and 1. Because the probability distribution is based on a discrete random variable, we will not use class boundaries for the horizontal scale, but rather the bars will represent each discrete value. So whenever you create your table, your chart, like your histogram, this is going to represent x, and this is going to represent p of x. So p of x, the highest that you can have is 1. So it goes from 0 to 1. because all px are between 0 and 1. And the sum of all of them will add up to equal 1. So an example would be, let's say our random variables are 0, 1, and 2. You'll have some bars here that represent the probability. And all of those should add up to equal 1. So this is what the probability distribution chart will look like. The vertical scale shows probabilities instead of relative frequencies. So that's P of X, that's your probability. So that's your vertical scale. Your horizontal scale will represent each random variable. So let's look at this example. Does the table on the right describe a probability distribution? So we have X and P of X. So it looks like it's a random variable. Do all the P of X add up to equal 1? Yeah. Summation of P of X is greater than 1. So this is not a probability distribution. Because if you add those up, it's like 1.7. Example 2, suppose we have a function for a probability distribution where P of X equals X over 3, where X can be 0, 1, or 2. Does this function follow the requirements for a probability distribution? So let's create the table. This reminds me of algebra. So it says where X can be 0, 1, or 2. And the function is X over 3. So this one would be 0 over 3, which is just 0. So probability of getting a 0 is 0. Probability of getting a 1 would be X over 3, so 1 over 3. Probability of getting a 2 would be 2 over 3. So if we look back at those requirements, the requirements are there is a numeric random variable of X and its values are associated with corresponding probabilities. Number 1 checks out. Number 2 says the summation P of X equals 1. What is the summation of P of X? All of the probabilities added together. 0 plus 1/3 plus 2/3? 1. It equals 1. So that's good. It is probability distribution so far. Number 3 says all of your probabilities are between 0 and 1. And it can be equal to as well. Are they all between 0 and 1? Mm-hmm. Yep. So if all of these check out, that means it is a probability distribution. So yes, it is a probability distribution. We are going to create a probability distribution using the table of the Mexican American jurors. So let's look at our horizontal axis, which is X. It's our random variables. And our Y, our vertical scale, is P of X. I'm just going to go like this. So I know, like, that's what it's like quadrant 1 for your histogram, if you want to look at it that way. So X is all of our random variables. Our random variables are how many jurors that were selected that are Mexican American. So we would make each box represent that. So go ahead and put your numbers underneath the box. All right, so we've done the X scale. So now we need to go to the probability P of X scale. So we look at the range to see what's the highest that we need, which we talked about that earlier, is 10. Mexican Americans got 0.28. So the highest that we need here is 0.28. It's just a tiny bit above. So let's see, how many are there? 7. So how much should we make each? What do y'all think? So it's just like in algebra where you're trying to set up your scale. What should we go by? If our highest is 0.283 and there's 7 of them. If we do 0.4, we'll get up to 0.28. And it's just like right there. So I think going by 0.4 would work. Or you can go by 0.5. I'm going to go by 0.4. Shouldn't that be 0? There we go. 0.04. And then 0.24 and 0.28. All right, so the first 0 through 3 is 0. And then 4 is 0.001. So it's like barely anything. 5.003, be like barely anything. 6.016, so be a little bit more. 7.05, so we actually go a little bit above 0.04. Then 8.133, so it's a little bit above 0.12. .236, so that'll be close to 0.24, right? And then 10.283, so that's just right there. And then we're going to decrease now. 11 is 0.206. And then 0.069. Bring it on down. Okay, so it's a left skew. See how it has a long tail here? So something that we probably didn't think too much about was when they first introduced this example, they said 80% of the population is Mexican American. So the probability of getting a high number of jurors that are Mexican American is pretty likely. Let's go to the next page. Example. The following table describes probability distribution for the number of girls in 2 births. So X represents number of girls in 2 births. So let's think back to what the sample space is. Boy, boy, girl, girl, boy, girl, and girl, boy. So this is where this probability distribution comes from. Probability of getting 0 girls would be this just getting a boy, boy. So the probability of getting boy, boy is 1 out of the 4. So that is where the 0.25 comes from. And then probability of getting 1 girl, here, either having a boy, girl or girl, boy, that's getting 1 girl. So that's 2 out of the 4, which is 1/2. So that's where that comes from. And then the probability of getting 2 girls, theoretically, is just 1 out of the 4 possibilities. So that is where this comes from. So to make this probability histogram, this would be X, this would be P of X. So your horizontal would be the 0, 1, and 2. And then your vertical would be 0.25, 0.5, 0.25. We could do like, I'm just going to make this go up to 1 and then do 0.5 and 0.25. So probability of getting 0 would be 0.25. Probability of getting 1 is 0.5. Then the probability of getting 2 girls is 0.25. Okay, so that I'm going to break up 5.1 into 2 parts. So we're done with part 1. Tomorrow we will talk about mean, variance, and standard deviation of a probability distribution.